Assalamu alaikum. Good evening, ladies and gentlemen, respected guests. It's a great pleasure to have you all here tonight. I'm delighted to welcome you in tonight's lecture within the series of London lectures, that's how we call them, organized by the Al-Furqan Center for the Study of the Islamic Manuscripts at Al-Furqan. Before I give the floor to the keynote speaker tonight, as you know, with us tonight is Professor David King, which we are honored to have him among us. I'm delighted to invite first Mrs. Sarah Yamani. She's a member of the YCCT, we call it the Yamani Cultural and Charitable Trust. It's an overseeing body. I would like to invite her to say a few words and to welcome you on behalf of the Trust and its chairman, His Excellency Sheikh Ahmed Zaki Yamani. So please start.
Assalamu alaikum. Good evening. Respected guests, ladies and gentlemen, I am delighted to welcome you all on behalf of my father, the chairman of Al-Furqan, His Excellency Sheikh Ahmed Zaki Yamani. And on behalf of the trustees of the YCCT, Yamani Cultural and Charitable Foundation, Trust, a body that oversees the work of Al-Furqan. It is great pleasure to see you all here tonight, and I'm honored to welcome you all. This lecture is part of Al-Furqan public lectures, which aim to strengthen links with those who are interested in the Islamic heritage, and to raise awareness about the richness of this shared heritage. Beside many conferences, symposia, and training courses, over the last 3 decades, Al-Furqan has organized more than 60 lectures on different aspects of Islamic heritage, culture, and civilization, such as codicology, paleography, critical edition, bibliography, history of science, arts, architecture, etc. Tonight's lecture will tackle a topic which is considered a cornerstone in the field of Islamic heritage, tradition, and studies, namely the field of astronomy. Muslim scholars throughout the Islamic era devoted considerable energy to many aspects of astronomy, including the aspects related to religious practice, such as the lunar calendar, the Qibla, and the Salah. I cannot think of a better person to speak about this topic than Professor David King, a world-renowned authority in this field, who is also an old friend of Al-Furqan. And we are honored to have him with us here tonight. And I would like to thank him for all his contributions and continuous support to our foundation's projects and activities. This lecture promises to be very informative and enlightening, and I thank you all for joining us this evening and look forward to welcoming you again to future events. Thank you.
Thank you, Sarah. Indeed, tonight's lecture promises to be a very informative and very enlightening. Professor David King, through this lecture entitled Astronomy in the Service of Islam, will take us into a long scientific journey. It will take us to the main milestones that characterized the studies in this field, which is the field of astronomy, during the Islamic era, obviously. The most important findings in this field during this era and the impact and the influence that such findings had in the advancement of the science in this field later on. Before I give the floor and we start with the lecture, I would like to say a few words about Professor David King. David King is a British-born Orientalist who has spent his academic life researching the history of Islamic astronomy, both folk astronomy and mathematical astronomy. He first studied mathematics at Cambridge University, then education at Oxford University, and worked with the Sudanese Ministry of Education. Then, as he likes to put it, he went medieval and studied Near Eastern languages and literatures at Yale University. His research is based mainly on medieval Arabic manuscripts and instruments, He spent 20 years in the UK, 10 years in the Near East, 10 years in the United States, and close to 40 years in Germany and France. He was project director at the American Research Center in Egypt, professor of Near Eastern Languages and Literatures at New York University, and he is now emeritus professor of History of Science at Frankfurt, Johann Wolfgang Goethe University in Frankfurt. His numerous publications include 5 variorum volumes: Islamic Mathematical Astronomy, Islamic Astronomical Instruments, Astronomy in the Service of Islam, Medieval Islamic Astronomy and Geography, and Astrolabes from Medieval Europe. His major works are world maps for finding the directions to Mecca, published in 1999, in part published by Al-Furqan, supported as a project, which we have been delighted, and in synchrony with the heavens. Astronomical timekeeping and instrumentation in Islamic civilization, published in 2004-2005. His publications can be downloaded at an online platform named davidaking.academia.edu. I'm honored and delighted to invite Professor King to address this distinguished audience tonight. So please, Professor, join me in that floor.
Good evening, ladies and gentlemen. Can you hear me at the back? Are you sitting comfortably? I asked Saleh not to exaggerate, and I am under constraints this evening. I have my wife here who told me not to talk too much about astronomical tables, and I have a former student, a former colleague from Frankfurt, Silke Ackermann, now at Oxford, Museum of History of Science, who has told me not to be nasty about various colleagues, some of whom I mentioned last time I was here a year ago. I'll try not to mention them this time. It's also a pleasure to have part of the family here, but I can't. Yeah, right. Okay. My story begins in Arabia, where even in pre-Islamic times the Arabs were concerned with a simple but comprehensive folk astronomy based on what one can actually see in the sky. But then, in the early 7th century, there appeared the Prophet Muhammad and the Quran, with its injunctions relating some of the pillars of the new religion of Islam to astronomical phenomena. The Muslim world grew from small communities in Arabia until after just a few decades it looked like this. Particularly the contacts with the Byzantine world, the Iranian world, and the Indian world were fruitful for the recovery of scientific traditions that very soon became a truly Islamic scientific tradition, with Arabic as the language of science. And it should not be forgotten that the Arabs themselves had their own tradition of folk astronomy. In all of the major centers of Muslim civilization, the study of astronomy flourished. Indeed, it was the queen of the sciences, practiced by the Muslims. And our task as historians of Islamic astronomy is to piece together the different chapters in that history from the available sources, which are mainly manuscripts and instruments, such as you see here in the observatory at Istanbul. These sources are now scattered in libraries and museums around the world. One of those manuscripts from the Istanbul Observatory, one of these, from the library, private library of the director Taqiyuddin, is particularly close to my heart, because It formed the subject of my doctoral dissertation almost 50 years ago. A manuscript from Leiden. Our investigations helped to bring the works of the Muslim astronomers back to life. This fanciful Ottoman miniature from the Topkapi of the greatest Muslim astronomer, the 10th century Egyptian Ibn Yunus. I say he's the greatest because I wrote on him, but he was the greatest. Presenting the Fatimid Caliph al-Hakim with a copy of his monumental work, the Hakimi Zij. A Zij is an astronomical handbook full of tables and astronomical and explanatory text. And Ibn Yunus' Zij was actually several times larger than the book that you can see here. The Caliph does not look too happy, but he should have been. You will hear much talk about the Zijs of Al-Khwarizmi and Al-Batani. Everybody hears about them. But there are only 2 out of over 200 Zijs compiled by Muslim astronomers between the 8th and the 19th century. I will not talk about Zijs tonight because my wife will not want to hear that. I will talk about tables for other purposes. One of our colleagues in Beirut used to call what we did, my teacher Ted Kennedy and myself, zigging about. Astronomy developed on 2 completely different levels in Islamic society. The astronomers worked with instruments and observations and calculations. But there were also the Muslim legal scholars, or fuqaha, Sunni and Shi'i, who worked only on what we call folk astronomy, that which we see in the heavens with the naked eye, in modern Arabic ilm al-falak al-taqlidi. They also favored a sacred cosmology, al-hay'a al-sunniyya, based on the Quran and the Hadith. Inevitably what they proposed, these fuqaha, was, on practical matters, was different from what the astronomers proposed. Much of the written tradition of astronomy began in Baghdad, Medinat as-Salam, which in the 9th and 10th centuries was the most civilized city on earth. It was, I have an Iraqi friend here in the front. Right, yeah. It was a city of learning and of books. The 10th century bibliographer Ibn Nadim compiled a list of all the books known to him in Baghdad, or in the Baghdad of his time. Many of those books are lost for all time, but at least we have their titles. Ibn Nadim treated all aspects of contemporaneous astronomy, scholarship, including, of course, astronomy and mathematics. And here are some of those books. Up here. They cover the entire spectrum of Muslim learning. And these books in Baghdad are here pictured in a manuscript of the Maqamat of Al-Hariri. Ibn Nadim, unlike some modern scholars, was also interested in makers of scientific instruments, and he listed 30 astrolabists known to him in Baghdad. Unfortunately, some of their instruments have been preserved, and this one showed up in Sotheby's in London 10 years ago and was published immediately, and it was made in Medinat as-Salam. Talk more about this later. Of the vast corpus of Islamic manuscripts relating to science and focus science, we are going to concentrate on those dealing with 3 subjects: the organization of the lunar calendar and religious festivals, the determination of the sacred direction towards the Kaaba in Mecca, the Qibla, and the orientation of mosques, and the regulation of the 5 daily prayers whose times are astronomically defined. I call this small but very important chapter in the history of Islamic science, Astronomy in the Service of Islam. People don't like it. Historians of Western science are not interested to know what the Muslims did for themselves. It's curious. The Muslims are not interested either. You can write what you like about the traditions of what they did in the Middle Ages, but there's been no reaction whatsoever from the Muslim world on this. Some people don't like non-Muslims working on this material, but nobody else works on it, so I was happy to do this. We begin with the regulation of the lunar calendar. Here is a miniature of the astronomer Taqiyuddin observing a comet on the first night of Ramadan. You see the new moon, it's the first night of Ramadan in the year 1577. The legal scholars in general were happy to rely on witnesses who actually saw the crescent on the first day of the month of the civil calendar. In medieval times, this procedure worked better than it sometimes does nowadays. For the medieval astronomers, on the other hand, the determination of the possibility of sighting the lunar crescent was a complicated problem. And here the sun is setting over the western horizon, and the moon is going to set a few minutes later. The question is whether the elongation between the sun and the moon is sufficient that the crescent be large enough that it be seen. And that also depends on the time between sunset and moonset, which is measured on the celestial equator, the maqth in Arabic, the delay between the two settings, and of course also how high the moon is in the sky. Yeah, all very complicated. But if these conditions were satisfied, the conditions that they formulated involving the apparent distance between the sun and moon, the difference in setting times, and the altitude of the moon above the horizon, if they were satisfied, then the crescent would be seen. If not, then it would not be seen. Here is the earliest known table for lunar crescent visibility. It was compiled by Al-Khwarizmi, who is famous because he wrote a book on algebra. So he's the greatest early Muslim mathematician. But that's not so. The book that he wrote on algebra was one of several that were available. Algebra was known to the Babylonians. And what is important about Khwarizmi is his astronomy, especially works that were discovered in the 80s and 90s in various libraries, including in Central Asia. This one tells you all you need to know about Ru'yat al-Hillah. Each month of the year, or each zodiacal sign, there is a number here, degrees and minutes. If the elongation of the sun and moon is that amount or more, the crescent will be seen. If it is less than that, it will not be seen. Now, these, by the way, are the numbers that you find in every astronomical table in the Arabic sources. The abjad, A, B, C, D numbers that were used before Islam by the Greeks and the Hebrews, and during the Islamic period, and later in medieval Europe. But today in modern Europe we have forgotten about 60 as a number, and about representing numbers by letters. I've mentioned another name of Khwarizmi to show that he didn't come from Central Asia. He came from Al-Qutrabul, you know where that is? Yeah, just outside Baghdad. And he was born there, otherwise he wouldn't be called Al-Qutrabul. Many people say he came from Khwarizm. In this Egyptian table for 1229, you're getting used to tables now. Yeah. For 1129 Hijra, and it's one of a series for each Hijra year, calculations have been made for the first day of each month of the civil calendar. There are two Islamic calendars. There's a civil one and there's a religious one. And if the moon is not seen on the first night of the month, then it'll be seen on the next night. What you have here is for this particular year, 1229, you have for each Muslim month, you have the where are we? The latitude of the moon. The Qaws an-Nur is the distance between the sun and the moon, and important too is the delay between moonset and between sunset and moonset, the makth. And then you have a prediction at the end of every line. It will be seen ghaliban, right? Generally it will be seen, or la yura abadan, it will not be seen at all. So you have to wait till the next day to begin the month, the religious month. Or asir ru'ya, it will be difficult to see. And we have several years of this table to see how they did it in the late Muslim period. In brief, the achievements of the astronomers in this domain were impressive indeed. By the way, there's an article in that book there, the Encyclopedia of Islam, Ra'at al-Hilal. All this is there. And some of the subjects treated here are already in the encyclopedia. Our second topic concerns the sacred direction, or Qibla, towards the sacred Kaaba in Mecca. And here we look first at what the astronomers did, and then at what the fuqaha did, because that's the way I did it. I came to the Islamic methods of calculating the Qibla, and later, when I realized there was a problem, I went to the legal sources and found something else. So the object of the exercise for the astronomers was to find for any locality X, to find the Qibla, the direction from the local meridian, north-south line, to Mecca. And to do that properly, you need to know your own latitude, the latitude of Mecca, and the longitude difference between them. Then you can also calculate the distance to Mecca using the same formulae, but here look at the formulae. These are not for softies. These are serious trigonometric formulae which were solved already in the 9th century by Muslim scholars, mainly in Baghdad. But there are many solutions, and there are many variations, and there was enough of a problem to keep Muslim astronomers going for 1,000 years. It's not trivial. We have from Baghdad, 825, a solution by solid geometry, which blows the mind, because this is only 200 years after the death of the Prophet. And they are dealing with solid geometry, of which there was no previous tradition of this kind. And there is a modern interpretation of the same problem. And this is too complicated for normal people. And so Al-Khwarizmi, God bless him, he made a table of Qibla values in degrees and minutes for each degree of longitude difference from Mecca and each degree of latitude difference from Mecca, and that's the Qibla in degrees and minutes. Not bad for the 9th century. The ultimate solution, one of the ultimate solutions to the Qibla problem is a table. You're not getting tired of tables yet. No. Table by the 14th century Damascus astronomer Shamsuddin al-Khalili. Discovered 50 years ago in a Paris manuscript, and other manuscripts are available, particularly in Damascus and Cairo, Berlin. The table shows the Qibla in degrees and minutes for each degree of latitude, 28, 29, 30, 31, 32, so on. For each degree of longitude difference from the meridian of Mecca to the east and to the west. And so what are written here are actually longitudes to the east and to the west. These values are so accurate that we have been unable to determine how al-Khalili computed them. We had in Frankfurt a few years ago a man who is the expert on medieval tables, Glenn van Brummelen of Canada, and he spent a lot of time on al-Khalili's tables without being able to crack them. The way you crack them is not by looking at the actual values. You don't look at those, you look at the errors and see how was it possible to reproduce these error patterns. And I couldn't do it, and he couldn't do it, and so it's still open. Another ultimate practical solution was the geographical table compiled in Kish near Samarkand in the mid-15th century. This gives the longitudes and latitudes, longitude and latitude, and Qibla, called here Inhiraf to the meridian, and also the distance to Mecca, for 250 localities from Al-Andalus to China, together with their Qibla directions and distances to Mecca. This table was discovered in an 18th century manuscript copied in Karbala, preserved down the road in the British Library. This kind of information was often engraved on later instruments. Astrolabe is actually early 10th, 11th century, where you have the Qibla for Isfahan shown on the back of an astrolabe made in Isfahan. And then these later Safavid Qibla indicators and an astrolabe in the British Museum, where the Qiblas and the directions to Mecca are all written out in words. Okay, that's quite a lot of reading. Now, we come now to the way the Qibla problem was solved by scholars who saw no need to actually calculate the Qibla. They knew very well that the rectangular base of the Kaaba is actually aligned in certain significant astronomical directions. Basically, you could say the four corners are in the cardinal directions, north, south, east, west, but that's not quite correct. The Kaaba is the Canopus was a south indicator for the pre-Islamic Arabs. South in the sense they knew where south was, but they also liked the direction of the rising of Canopus, the brightest star in the southern heavens, and lo and behold, that defines the major axis of the Kaaba, which is a rectangular base, not squares, some people think. It happens for the latitude of Mecca that these two directions, the major axis and the minor are perpendicular. Summer sunrise, winter sunset down here. And then also from Islamic, pre-Islamic meteorological folklore, also linked the four winds with the sides of the Kaaba. I like this one in particular. The east wind was still called the Qabul. That's a very interesting fact. And this was discovered in the 80s, and what was discovered in medieval Arabic texts was confirmed by satellite images. Now, in these same legal texts or folk astronomical texts or basic geographical texts, we find schemes like this. Also encyclopedias, we find pictorial schemes linking the sectors of the world. This defines a sector with the sides of, with part of the perimeter of the Kaaba. We have 20 different schemes, and these are 12 sector schemes and 72 sector schemes. These schemes also tell you which direction to face, which astronomical direction to face the Kaaba. See, the astronomers were saying you face Mecca, calculate the direction of Mecca. The legal scholars were saying, no, I'm not interested in the city of Mecca, we're interested in the Kaaba. This is what's said in the Quran. We want to face the site of a building that you cannot see. So where is this Kaaba? Well, it helps to know what the Kaaba actually looks like and represents. And that helps you when you're in Andalus or in China to choose the appropriate astronomical direction. Historians of Islamic architecture have wondered for a long time about the often curious orientations of medieval Islamic religious architecture. Some of them have wondered why some medieval mosques do not face the modern Qibla directions. These colleagues are beyond hope, because you cannot expect a medieval mosque to face Mecca in the way you would build a new mosque today. We are getting closer with other people who recognize that these mosques are not always in the Qibla that was calculated by the medieval astronomers. There were other considerations, such as mosques being built on the foundations of earlier religious architecture in Jerusalem, in Damascus, in Cordoba, for a start, but others were laid out in directions defined by astronomical horizon phenomenon. The sun goes up there in midwinter or goes up there in midsummer. This will do for the Qibla because the Kaaba is the way it is. That's what happened. These are three cities on which we have textual evidence, and which present some problems and need to be compared with existing mosques. The situation is so complicated that some modern writings on orientations are not to be believed. I'm going to be nasty again. Such as the book showing that the earliest mosques faced Petra and not Mecca. as I said, not to be believed. This is all nonsense. These mosques all face Mecca. Every single one of them faces Mecca, whether they're facing south or east, or they were built to face the Qibla. And only rarely did this difference between the Qibla directions proposed by the legal scholars and those proposed by the scientists lead to conflict. Some legal scholars accepted for the Qibla either the actual direction of the Kaaba, there's the Kaaba, and here's the direction from the person who's standing looking at the Kaaba. You should face this direction. But it's also legally acceptable for you to stand there facing the Kaaba, but anywhere in between 90 degrees is acceptable according to this particular manuscript from Oxford. Rarely did it happen that a mosque had to be pulled down and rebuilt in a different direction. One very good example from Wasit in Iraq was aligned first towards winter sunset, and that was pulled down, and a new mosque was oriented in the direction computed by the astronomers in the 9th century. The third aspect of astronomy in the service of Islam relates to the times of the 5 daily prayers. These are defined by the position of the sun above or below the horizon. Everybody knows that Muslims pray 5 times a day. But how did they do this in the medieval period? And why are these prayers astronomically defined? Particularly the daylight prayers in terms of shadows. Here we can differentiate between simple procedures for all and highly sophisticated procedures in some of the principal scientific centers. The Islamic day begins at sunset, the Maghrib prayer, because the calendar is based on the visibility of the moon at sunset. The second prayer is the Asha at nightfall. The third is the Fajr at daybreak. The fourth is the Zuhr at midday, and the time of the fifth prayer, the Asr, is regulated by means of shadows. The shadow of a vertical gnomon, miqyas, is minimum at midday. There's the gnomon, and there's the minimum shadow at midday. The Asr begins when the increase in the length of the shadow is equal to the length of the gnomon, and ends in some circles when the shadow increase has become twice the length of the gnomon. In Maghribi and Andalusi practice, the Zuhr prayer begins when the shadow increases 1/4 the length of the gnomon. We may well ask why. The muezzin can use simple shadow observations by day. Here's a gnomon in the mosque of Janad in the Yemen, and here is a simple set of shadow lengths, midday shadows of a person for each month of the year to regulate the Zuhr and to start to regulate the Asr. I just hope that this gnomon is still there, and I just hope that this mosque is still there, and I just hope that Jannat is still there. The muezzin could also use simple arithmetical procedures using the lunar mansions, the manazil al-qamar. But already in the 9th century, the astronomers introduced mathematical solutions. And the earliest known table for regulating the times of the Zuhr and the Asr is, of course, from early 9th century Baghdad. And it's our friend Al-Khwarizmi who prepared a table for the latitude of 33 degrees, which is Baghdad, giving in these titles here, giving the name of the zodiacal sign, that's for each 30 days, the beginning of the Zuhr, the beginning of the Asr, the end of the Asr, and that's the argument. This is a very nice table, the first of its kind. And here is an extract from the tables from the prayer time, for the prayer times at the latitude of Cairo, prepared by my friend Ibn Yunus around 1000. You know those tables, those little tables you used to find on the wall in Muslim houses and places, giving the prayers for each day. And they were the modern solution to this problem, and this is the medieval solution. This is much more impressive because it was done by hand. And I rather like these tables. I hope you can stand one or two more tables. I have to ask my wife any more. Yeah. Try. Okay, we're getting to the end of this, particularly in Egypt, but also in the 13th century and Syria in the 14th. The office of mosque astronomer or muwaqqit flourished. This is an extract from a Paris manuscript of the splendid set of tables by my friend Shamsuddin al-Khalili, muwaqqit at the Umayyad Mosque in Damascus. For each day of the year, each degree of Capricorn here, he tabulated all these functions. These are all complicated trigonometric functions. And what has he got here? He's got the operations of the times of day and night for the latitude of 33 degrees 30 minutes, yani Damascus. And he's got, for Capricorn, he's got the maximum altitude of the sun, half the length of daylight, the hours of daylight, the altitude of the sun at the Asr, the time of the Asr, and he's got the length of night and the duration of morning twilight here and evening twilight and more besides. All correctly computed to the nearest 4 minutes. Now, my wife is getting anxious, but we're almost there. Muslim astronomers were not only interested in the times of prayer. They compiled tables for finding the time of day by the sun and the time of night by the stars. And here's an extract from a 10th century table, again preserved in Paris, for finding the time of day by the sun computed for the latitude of Baghdad, 10th century. You feed in the maximum altitude of the sun, and you feed in the instantaneous altitude of the sun, and you get the time. We have numerous tables of this kind for different cities throughout the Muslim world. Muslim astronomers contributed to astronomical timekeeping. I recently published a description of the tables used in medieval Jerusalem, published by Muslim Heritage, and I thought the time was ripe. As a gentle reminder that Jerusalem was a Muslim Arab city in the Middle Ages, up to the 20th century. A fact that some people seem to have forgotten. There are two people I wanted to dedicate this to. One cannot read and cannot think, and so will forget the Donald. And Netanyahu, I would like to dedicate it to him, but he'll be in prison and so it would be a waste. So I put it on Muslim Heritage, thanks to the boss. What have we got here? The tables date from the 14th century and contain 20,000 entries. That means it's a book like that. They're for finding the time from the altitude of the sun throughout the year and regulating the times of the 5 daily prayers. Before the discovery of these tables, it was not known that there was ever any serious astronomical activity in Jerusalem. Well, there was. The manuscript here is from Leipzig. Second, different part of the same corpus from Princeton, and one manuscript from Cairo. And today I was talking with Celeste, the librarian here, about the possibility of some of the things that are in the Khalidiyya catalogue that I cannot access, but I have the catalogue, whether it's possible to get some photos. Maybe there's even more there. I would hope that we might find a couple more copies. The main thing is we have one copy of each of the 3 parts of this corpus. So, Muslim astronomers contributed to astronomical timekeeping for close to 1,000 years, and I have tried to document their achievements for the first time. This book, In Synchrony with the Heavens, the title sort of summarizes Islamic astronomy. That's what it was about. It includes surveys and analysis of all sorts of tables for timekeeping, based on over 500 manuscripts. I gave it the subtitle, The Call of the Muezzin, and there are 700 pages of text dealing with Islamic tables. That really is too much. But I had to do it, and why not? Some people say they don't like tables, and they say if you've seen one, you've seen them all. This is very short-sighted. As far as I know, the book has had little influence, and so I've recently put the whole book on my website, so anybody can download it for free. A colleague of mine recently published a book on perceptions of time in the Islamic world. She thoughtfully included a reference to my survey. My survey of 1 millennium of activity by Muslim astronomers and legal scholars in astronomical timekeeping using tables and instruments. Her discussion was packed into 1/2 of 1 sentence. It blew my mind. I've tried to give an introduction to what Muslim astronomers did in the way of astronomy. It's one small chapter in Islamic astronomy. There's so much more, but this is all we'll discuss today. Or is it? In brief, they produce all manner of tables and all manner of instruments, mainly for astronomical timekeeping. Their achievements were considerable, and now that they are documented for the first time, the history of Islamic astronomy looks very much richer. Thank you. Now, as in the campaign against obesity, the British government is trying to forbid people like Tesco to offer 2 for the price of 1 because it makes you fat. I read that this morning. Now I can stop and go away, but it so happens that I never talk about transmission because there are so many people who talk about transmission of Islamic material to medieval Europe. And of course, most people love the Greeks more than anybody else, so Greek science in Islam into Europe, they love it. So if you will permit me, I could speak for another 20 minutes on the European Renaissance and see if there was any Muslim influence there. Am I allowed to do that? Yeah. So, yeah, the end is not really the end, and here is a new beginning. And until the 1970s, scholars tended to be interested only in Islamic scientific material that was transmitted to medieval Europe. Now, I too am interested in European astronomy in the medieval and Renaissance periods, and I should like to show you a couple of dozen examples from the European Renaissance, side by side with instruments, earlier Islamic instruments of the same kind. I do this to annoy some colleagues. Okay? I do this to edify you. One of the conclusions you can draw is that maybe the Muslim contribution to astronomy is perhaps still a little underestimated. This is a new subject. The only other person who's talked about anything similar was standing right here a few years ago. George Saliba, my academic twin, has published a book about Islamic influence in the Renaissance. But he was only talking about planetary astronomy. He never talks about anything else. And I only talk about instruments and prayer times and things. So I thought, instruments. Renaissance. What do we mean by Renaissance? Whose Renaissance? There's a move afoot in the intellectual world to talk about renaissances involving other people. Were there any other? What do we mean by the European Renaissance? I like to define it as a sort of wake-up call. Europe woke up out of the Middle Ages and discovered that there was more. They were a bit late, but they rediscovered Greek texts, which had already been translated into Arabic, but they didn't know that. And they preferred to translate the stuff themselves. I'm going to get blasted later by a medievalist. Did you know there was a Renaissance in Islamic civilization? 100 years ago, the Swiss historian of Islamic civilization, Adam Metz, published his famous book, The Renaissance of Islam, focusing on the 10th century. And then you have King publishing on the internet on the occasion of the invasion of Iraq by the Jahili forces, writing the Renaissance of Astronomy in Baghdad in the 9th and 10th centuries. It wasn't an essay, it was just a short essay and then a long bibliography. And then you have my friend George Saliba writing on Islamic science and the making of the European Renaissance. So, Renaissance is in these days. This picture was printed in Germany in 1533. This is the Renaissance taking place. And these astronomers, some of their instruments are Islamic in origin. They didn't know that. Others are purely They didn't always know that. Others are purely European in conception. Most of them do not go back to the Greeks. They go back to the Muslims. We can understand the Renaissance achievements better if we know what our friends the Muslim astronomers themselves achieved. Please pretend that this miniature depicts them in Baghdad in the 9th century, Isfahan in the 10th century, Cairo in the 11th century, Cordoba in the 12th century, Maraga in the 13th century, Damascus in the 14th century, Samarkand in the 15th century. These were the capitals of astronomy in the Muslim world in those centuries. It is now common knowledge that the solar, lunar and planetary models of Copernicus were not original to Copernicus, but were somehow derived from Muslim sources. They don't look the same, but they are the same. His models for the sun, moon and planets are identical, mathematically identical, with those of his predecessor 150 years, the 14th century Damascus astronomer Ibn Shatir. Copernicus made one big mistake describing a model for Mercury that he obviously did not understand. And the reason he didn't understand it is that it wasn't his model. That was a big breakthrough when that was discovered. Much has been written on this situation and its consequences, mostly by George Saliba. And I will not dwell on planetary theory either today. Of course, Copernicus's proposal of a heliocentric planetary system was of more lasting significance. And few people are aware today that there were Muslim astronomers who proposed heliocentricity before Copernicus, but their works were not printed, and that's the difference between the Middle Ages and the Renaissance. I shall deal with spherical astronomy, the study of the apparent daily rotation of the sky around the observer. The observer is in the middle, you can't see him, but everything goes around this way. The sun rises here, goes up there, and then around the other side. This is the meridian, the north-south line, north-south on the other side, at the horizon. And you've got the celestial pole around which everything revolves, and that measures the latitude of the locality. If you know that the sun goes up in the morning and sets in the evening, you know something about spherical astronomy. But nobody cares about spherical astronomy anymore. That could be the subject of another lecture. And I met an American in Istanbul 2 weeks ago who was crying that spherical astronomy had been dropped from German school textbooks at the beginning of the 20th century, and that now nobody knows anything about this simple situation. Yeah, I gave a lecture in at the observatory in Tenerife 20 years ago to some doctoral students in astrophysics. I was asked to speak about Muslim things and tables and so on, and I mentioned latitude, and I got some funny looks, and I asked, how would you measure the latitude of Tenerife? And not one out of 20 students, doctoral students, had any idea how you would measure it. This is the new order. Now, what do we have here? Oops. We have more tables, but only 2 or 3 tables. Look at these tables. These are now Renaissance, well, post-Renaissance tables. This is early modern period. 1791, a book which is about this thick. The author, poor German astronomer and theologian Müller, complained that he had great difficulty in finding a printer for this book, which is about this thick. Now look at, well, in fact, the way he made some money was to change the front page, from German to French, because the same tables that would work for the whole of Germany would also work for the whole of France. So he doubled his income, just like that. But look at these tables. I'm almost finished with tables. These tables are for finding the time from the altitude of the sun or from the altitude of any star. Now that's mind-boggling. And our minds were boggled when we found one half of these tables that big in Cairo and the other half in Oxford. And I think that the surviving copy and manuscripts together is probably in the hand of the author, and probably nobody could be found to make any further copies. There are 500,000 entries in these tables, but they're better than the ones of Müller for Germany and France. Now, you all know about the astrolabe. If you don't, there's a very nasty article on my academia page entitled "What is an astrolabe?" That's actually the nice part. The bad part is what is an astrolabe not. And the second part contains a whole load of quotes from the internet. You have never read such rubbish put out by professors, students, theologians, the works. Nobody has a clue what this instrument is. It's a model of the universe that you can hold in your hand. There's the universe, the stars and the sun are right there on this this grid here, and they rotate over a series of plates which serve individual latitudes. Now these latitudes here are very flat. Most astrolabes don't look like that, but this astrolabe was made in the Yemen by a sultan, and the latitudes are 13 degrees, Aden, Taiz, Sana'a, and they all fit inside a very nice little mother, it's called, and you can set the configuration of the sky to the configuration of your horizon and your meridian, just like that, in seconds, and then you have a model of the universe, and you can do an awful lot with it. I tried to make a survey of these all the various Islamic instruments in the second volume of this book, In Synchrony with the Heavens, and since it was published in 2005, I gave it a silly title, Instruments of Mass Calculation. But we were dealing with others who were lying about instruments of mass destruction. And yeah, look at this French astrolabe. It's got two little dogs on the top. And look at this here. There's two pussycats. This is France, 1350. This is Baghdad, 985. There's some influence here. These are not the best examples I could have chosen, but we have nice pictures, and so we can say that, for example, these here are developed from the mihrabs which are common on Andalusi astrolabes from the 10th and 11th century. And we can say that these birds here are inspired by a tradition of zoomorphic star pointers that we find already in Baghdad. And there's a little circle here, and that circle is related to that quatrefoil on this Iraqi astrolabe. It's actually a Byzantine symbol, but it appears on early Islamic astrolabes. Not many, but some. And I find this rather impressive. For the art historians here, these cats, wild cats, big cats, are probably, I think, Sasanian in inspiration. You don't have to stand up. And this quatrefoil is Byzantine. Surely the early Muslims liked a quatrefoil. They put it, for example, on the walls of the palace of Mushatta. And then we have here smiley. Yeah. And Professor Al-Hassani, who is the author of 1001 Inventions, missed out this one. I think you should put him in. Okay. This is the first smiley. This is actually a representation of a lunar mansion, a beloved lunar mansion that was right here in between these two stars. And this is a very unusual early Islamic representation. It would be more reasonable to find a mihrab here, but they appear only on the Andalusian astrolabes. And anybody who doesn't believe me that this feature went into the Italian Renaissance, then there you have it, in exactly the same position, exactly the same function, namely decorative. Nothing religious, just decorative. Now, 30 odd miles west of here in Reading, there was a man called, what was his name? I should have written it down. I've forgotten. Blagrave, John Blagrave, who devised an instrument called the mathematical jewel. It's a universal astrolabe with this star map here and this construction of astrolabic curves. You can solve all the problems with an astrolabe that you can do with an astrolabe with one plate rather than a series of them. What Blagrave surely didn't know was that this was first devised in the 12th, 13th century in Al-Andalus, but at the same time there was a man, and I'm sorry I left out his name, Ibn Sarraj, who made this universal astrolabe, which is the most sophisticated astrolabe that was ever made anywhere. Not least because it is universal. You can see it has the same basic shape there, but it's got 12 plates inside that are devised in such a way that they can be used with the star map in 5 different ways for any latitude. There's owner's marks on the rim of this showing that it went to Cairo in the 14th century still already, and some astronomers said, I own this, I own this, I own this. And one of the astronomers, a man called Abdulaziz al-Wafa'i, he said Ibn Siraj made this very nice astrolabe, but he didn't write a treatise on how to use it. And so he wrote a treatise. He was a very competent astronomer, and he understood every single aspect of this astrolabe. And I'm afraid we haven't published it yet, but with my colleague François Charette, formerly of Frankfurt, we hope to publish this astrolabe and the texts. One from Cairo, which I found first, which only talks about the front and the back. And then I went to Oxford one day, and I found in the drawer of photos, I found pictures of 12 plates, and the instrument doesn't need any plates. So what's going on here? And the answer is it was made to boggle the mind. It was not very practical, but run it. Now, you get serious astronomical developments here. Regiomontanus was the greatest astronomer in Europe in the middle of the 15th century, and I got blasted by that, about that, by a French colleague who thought that Paris was still the center of astronomy in Europe, and it was Paris with the beginning of the century and Vienna in the middle, but don't forget Samarkand. And this plate that was found in an astrolabe of Regiomontanus type in New York is identical to a universal plate that is devised by Ibn Basso in Granada, 1300, for solving problems for all latitudes inside an astrolabe. And then astrolabes with lunar solar gear mechanisms. This one is in Greenwich, and this one is in Istanbul, I think, but it's Biruni writing in the 11th century on the same thing. This was not a Muslim invention. We had Greek instruments of the same kind that were transmitted to Islam and have not yet been properly published. I love the quadrant named Quadrant Vetus, old quadrant. This was the second most common instrument in medieval Europe. And it's obviously a European invention. It appears in the 12th century in Al-Andalus, amongst the Christian community, and in 14th century it was very popular. It has these markings which are a universal, approximate way of finding time. It has a shadow scale, and it has a movable cursor, a majorra, which you can move to adjust the latitude of the place and the time of the year, the solar longitude. Now, wouldn't you know, in a Cairo manuscript, Baghdad, 9th century, mention of the operations with the quarter of a circle. Anonymous, could be Al-Khwarizmi, could be somebody else. The latitude 33 is mentioned at the end, and 33 is nothing but Baghdad. And it says that the circumference of the quadrant is divided into 90 degrees, and there is a thing called a majorra. Yeah? And on some of the quadrants this is mutaharrika, and on some of them It is thabita. Some move, some don't. And also the curves that you saw on the quadrans Vetus are not the only way of representing time. And so we have 3 different varieties of quadrant and 2 different varieties of cursor, fixed or movable. 6 examples of the quadrant described already in 9th century Baghdad. So why didn't the Muslims use this for centuries? And the answer is they didn't like it, because it doesn't work exactly, it works only approximately. The Muslims preferred instruments like this one for Nishapur, but we have it already in texts in the 9th century Baghdad, and this one for Vienna. Okay, these are the same instruments. And this is the quadrans Vetus. This is all you need. You don't need the stupid cursor on the outside. It's not necessary. This is all you need, and that's all you find on these 10th century Baghdad astrolabes. And then these are the orrery quadrant for latitude 33, and these are trigonometric grids of 2 different types, and all these shadow scales that you find on every astrolabe for the rest of a millennium. Another thing which Professor Al-Hassani has not put in his book is the fact that the Muslim astronomers had graph paper in the 10th century. And this is not a 10th century example, but I have one. There is a Zija Safaya preserved in Berlin, a Zij, which is a Zij with plates, and that is an instrument, an astrolabe with plates inside which give astronomical Zij information about the planets. And on some of the plates there are these markings. This is 10th century. So, graph paper, please add it to your list. I found this one about a week ago. I couldn't believe, well, this one was Sotheby's 10 years ago. An instrument with a representation of serious trigonometric functions by the leading instrument maker of Baghdad, with a solar scale around the outside and calendrical scales, and these a set of 6 curves which are neither circular nor are they based on conic sections, so they're above that. And how did they do it? Well, we didn't know how Nastalos did it, because normally you would make a table of the function for every 10 degrees, then you'd mark for every 10 degrees on the instrument a dot, and then you connect the dots. But Nastalos didn't do that, because if you look more closely, there are no dots. I do not know how Nastalos did this. And nor does Glenn van Brummelen, who is the expert on statistics related to medieval astronomy. He drew these curves with a computer. The red ones and the green ones. The red is the accurate formula, and the green is the approximate formula, which is common. And we couldn't figure out which one was used. Nor could we figure out how they did the curves. Don't tell me you're tired of instruments. Because I got a few more here, and this is one I like best. Some of my English colleagues were not happy when I tried to show that a highly sophisticated medieval English instrument for timekeeping by the sun for any latitude, which was thought to have been invented in England, was actually invented in Baghdad centuries previously. The shape of the instrument in the form of a boat is not necessary to the function of the boat. What you do need, though, is a mast that you can rotate, and you have here on the main part of the instrument, which is this, you have here a grid which enables you to find time from the date and the altitude of the sun and the latitude. Yeah, it's a very complicated formula. It's all solved by one instrument. Now we have Latin texts and we have medieval English texts. There must be an English instrument. No, that's not the case. They do have boats in Baghdad. Mushkida? In Oxford we found a treatise by Habash, who was the leading astronomer in 9th century Baghdad, describing an instrument which was for finding the time of night by the altitude of various stars. And there is the instrument, and it works. And you don't make an instrument for finding timekeeping by the stars if you haven't already made a simpler one for timekeeping by the sun. But my English colleagues will never forgive me. The same holds for the most sophisticated calculating device from 15th century Vienna school. This is a universal timekeeping device by Regiomontanus, but he wasn't the first to put it together. We have here an Ottoman sketch of the same instrument, totally unique, but there's a little number somewhere, I don't know where, little number which says 23:35, 23 degrees 35 minutes. That is the obliquity of the ecliptic, the difference between the ecliptic and the equator, and that is a number which went out in the 11th century because the Muslims had better values, and certainly the Ottomans had better values by then, and so the 23:35 gives it away that this is an instrument that was conceived centuries before, like the 9th century. And wouldn't you know, I think it's Ibn Nadim has a Risala fil Amal bil Luh as-Sa'at. And what is that other than a Luh as-Sa'at? I'm getting tired too, but look at these. What's nice is the provenance. And I love sundials, but sundial freaks don't know that the Muslims had an incredible tradition of sundials and mnemonics. That's the study of sundials, theory and practice. And compare these two. This is the most sophisticated sundial I can find from the 16th century. But look at this one. Ibn Shatir, the head astronomer in Damascus, made this sundial. How did he do it? He made tables first. And with the tables you construct the curves. It's 2 meters long and 1 meter wide. Yeah, another favorite. Karl Scheu was my academic predecessor. He was a German historian of mathematics who was a school teacher and ended up in the University of Frankfurt, and then unfortunately died at a very early age. My first work was dedicated to Karl Scheu because he was concerned with the Qibla and the mathematical solutions, and he was so enamored of the subject he made a map, which he published in a geographical journal. And he said this is what it would look like if you had a map with Mecca at the center, and you could measure the distance and the direction to Mecca from any place on earth. See? Well, good. The year was 1989. This popped up at Sotheby's, and again blew my mind, because all I knew was that Shoei had done this before. And what is going on here? You have a map centered on Mecca with places you can't see the dots, but there are dots for places, and then these are the names from Cordoba over to Peking, and from the Yemen up to northern regions. Obviously Safavid, made in Isfahan, signed, made in Isfahan about 1650 by somebody who was completely unknown. This is the most sophisticated Islamic instrument we ever saw. It's totally mind-boggling. And that was, of course, my first, no, it wasn't my first contact with Al-Furqan, but you kindly said you would help change this from a book which would cost £500 to a book that would cost 50. And that was very considerate and a good idea. No more clocks. By the time we get to this kind of instrument, you have to say that the Muslims and the Europeans have come to a tie. That's it. Because these instruments are the same, but different in size, but this is what's going on here. It's a tie between the astronomers in Istanbul and the astronomers of Tycho Brahe in Denmark. However, the observatory in Istanbul marked the end of serious Muslim astronomy activity in astronomy. I said serious. Of course, astronomy continued into the 19th, 20th century. Finally, please look at the design of these star maps on the wreaths of these astrolabes from 16th century Flanders. This distinctive design occurs out of the blue. It has no known precedent in medieval Europe. Each one of these has a sort of cup here, a wine or glass. And why do you have this all of a sudden? Where does it come from? Compare it with this 16th century Iranian astrolabe star map. What do we find but the Basmala, Bismillahir Rahmanir Rahim, written in mirror script, one of my favorite Arabic scripts. Half the text is written backwards, and I would claim that this influenced European reads, star maps on astrolabes. Can you imagine that a basmala in mirror script might have influenced this design? You might say this shape here was like an open tulip, but tulips were not introduced to the Low Countries until the 17th century. In all of these examples, it was the Muslim scholars who derived the solutions before the Europeans, sometimes long before. Sometimes we can point to independent developments on the part of the Europeans. Sometimes Islamic influence is abundantly clear. Europeans started borrowing astronomical knowledge from the Muslims, texts, instruments, techniques from the 10th century onwards in Al-Andalus. Historians of medieval astronomy have for decades been publishing medieval Latin texts based on Arabic originals. It is well known that medieval European astronomy was heavily influenced by Islamic astronomy. Today you have seen how many Renaissance instruments were borrowed from or inspired by Islamic originals. In any case, we should have a healthy respect for the Muslim astronomers, for they were the leading scholars in their field from the 8th century to the 15th century, and their influence was far greater than most people realize. Thank you.
Thank you so much, Professor, for this fascinating journey. I do apologize for running a bit late, and I didn't dare actually to stop Professor, especially that the second part was very interesting as well. We have to cut short probably the discussion part. We planned initially a half an hour, but probably will turn it into 15 minutes if you agree. I'll take briefly a few questions. Just please kindly be brief in your questions so that Professor can. And I ask Professor kindly to stay a bit more, to remain on the stage.
I'm Mohammed Amin. I'm an amateur in all of these things. In Europe, heliocentricity, I understand, was resisted quite strongly by the Roman Catholic Church. How was heliocentricity accepted and spread in the Muslim world, or did it spread?
Okay, you are right about the Church's reaction to the book of Copernicus. It was on the forbidden list for 200 years. Fortunately, some people ignored that and went on and did this and that. In Islam, people did write about heliocentricity, but their works were not distributed. Their works were not sent to other parts of the Muslim world. A good summary is in the article Heliocentricity in Wikipedia of all places. I mean, they do mention the names, give some references.
Am I right in thinking that the Savage astrolabe you pointed out is in the Benaki Museum in Athens?
That astrolabe, the most sophisticated astrolabe ever made, is in the Benaki Museum, which contains the private collection of Benaki, who was a great Islamic art collector.
The similar astrolabe that you and I know, which was a copy of that, made in Lahore, I believe, does not have the 12 plates though. It's like
yeah, nor is it a real universal astrolabe in that sense. No. Mr. Sulzberger is referring to an astrolabe mater, the base of an astrolabe, which was sold in one auction house and catalogued by myself. And a few years later, the Reet, the stomach of the same astrolabe, showed up at maybe the same or a different auction house. Same. And the cataloguer overlooked the fact that he had already catalogued the other half. Nobody's perfect. But somebody very astute noticed the two parts belong together.
Our colleague, Tariq, please.
Professor King, thank you very much for that enlightening talk. I don't have a question as much. Oh, sorry. I don't have a question as much as a minor point that I'd like you to consider, which is very, very early on in the talk you bifurcated between folk astronomy and real astronomy. And although that assessment is probably accurate by and large, I think it's noteworthy to mention a few exceptions that we do have in our history, in Islamic history, scholars who transition between law and astronomy. And the person I have in mind when I'm saying that is none other than the heavyweight Maliki jurist Ahmed ibn Idris al-Qarafi. Anyone familiar with the field would know that name.
Yeah.
And he's got a monograph on this. But also the interesting thing is in some of his works, he stipulates that it's an obligation upon jurists who discuss these issues, because these are perennial issues among Muslims. When does fasting begin? When does it end? When does Ramadan begin? When does it end? He stipulates that it's an obligation upon those jurists to acquaint themselves, to learn this science. So I just thought it'd be nice to mention that there are exceptions, few as they may be, but they do exist. Thank you.
You're absolutely right. You used the wrong word, though. You said folk astronomy and real astronomy.
Yeah.
No. Folk astronomy and mathematical astronomy. Folk astronomy means shadows on Earth. It means horizon phenomena, risings and settings. It's very much concerned with the anwa, which are so complicated I'm not going to talk about them. But my point is that it was a complex system. I use the word comprehensive. It was comprehensive. And thank heavens, we have Ibn Qutayba, who wrote a book on Kitab al-Anwa. And that's all pre-Islamic Arab astronomy and meteorology. The two go together. That's why the winds hit the side of the Kaaba. It's not just the stars, it's the winds. Now, to your point, Al-Qarafi, yes, I wrote an article which I should single out for you on people who were interested both folk astronomy and mathematical astronomy. And the place where that happened was the Yemen. Yemeni astronomy is a fabulous story, and fortunately we have 100 Yemeni astronomical manuscripts, and many of them overlap folk astronomy and mathematical astronomy. I had a doctoral student who went through 3 big folk astronomy texts by lawyers, fuqaha, and extracted all the information on the Qibla and the prayer times, 2 volumes, that dissertation in Frankfurt, now published by Brill. Petra Schmiedel is her name, I'll give you details. Most historians of science are not interested or don't know anything about folk astronomy. I became aware of it as soon as I'd written that article Qibla in the Encyclopedia of Islam. My last sentence is, some medieval mosques appear to be in directions that are not the directions proposed by medieval astronomers. But I don't know why. And then in the article Mecca as Center of the World, I presented the evidence from folk astronomical texts and encyclopedias why this was so. We should talk more about this because I opened a website recently and put all my stuff on it, and I have a very nice article, Islamic Astronomy, published by the British Museum at the end of last century, and you get about 3 readers in a month. And nearby is Islamic folk astronomy in the service of Islam. I got dozens of readers. There is interest. There should be. Somebody should translate Ibn Qutayba, and somebody should translate all of the other stuff. Now, this one that I showed, this legal text, is not by Kharafi. It's by a guy called Ad-Dimyati. Same period. Very early, very, very intelligent. He's saying this because there are problems, people don't know which direction to pray in, and he says this is the rule. And this Ayn al-Kaaba and Jihat al-Kaaba is very sensible stuff. Yeah. Thank you for the question.
I would like to
close by this. Please do join me in thanking Professor David King for being with us tonight and for such an interesting, informative, and inspiring lecture. Thank you so much. It's been a great pleasure. And thanks also to you for being with us tonight, and we very much look forward to see you in our future events. So if you don't mind, anyone who hasn't been registered before, do leave your email or any contact details so that we could keep you updated for future events. Thank you so much. Have a please.
My last words to you.
أي خدمة.
Have a nice evening and see you next time, inshallah. Thank you so much.